Hello students and YouTube learners. This is your friend Dr. Satish Singhal, PhD, Professor of Computer Science at El Camino College, Torrance, California. In the previous video, we laid down the foundation for IOAA technology. IOAA stands for Input-Output Analysis and Algorithm. In this video and next one, we show you a concrete example of using IOA technology and then writing a source code, running it and testing it based on that. So watch the video and pause it when you need to reflect and think. So basically in this video what we're going to show you is that software development always starts out with a problem statement, and that in itself could be a major thing because many times customer, internal or external, may not be able to identify problem exactly. We will not consider that. We will consider a problem well defined, but that itself sometimes is a major part of the software development. So after problem identification, we will map out all the inputs. We will name the input variables, we'll determine their data type, and then whatever we need to output, we'll map that out, the names, data types, and then we will analyze all the formulas that will be used in computation. We'll see their C++ form as well as the math form, and there are some surprises in there. We'll look into those. And then after analysis, which is in this case analyzing the formula, we'll develop something called an algorithm, which is a step-by-step procedure to complete software action in finite time. Okay, so sit back, relax, get a cup of water, and let's start this. So problem statement is central to developing IOAA for a software. System analysts have a whole field called requirement analysis that expands and strengthens the problem statement. Problem statement gives programmer the clues for what are the inputs and what are the devices making inputs and what are the required output specifications. More the software does, longer, multifaceted, and complex will be problem statement. Here I might have just a 3-line problem statement. In a big software like a information system for a company, my problem statement might be 50 pages with sections and subsections. Okay, so right now we're going to start with a very simple problem to illustrate IOAA technology. As complexity goes up, statement will be more pages, analysis will be more pages, and so on. So we want to find out surface area, volume, and weight of a solid cuboid. Cube has all 3 dimensions to be same. Cuboid has 3 dimensions that could be different. So here's our problem statement. Write a computer program to compute the following for a cuboid: its surface area, volume, and weight, assuming that it's a solid cuboid. And then print the followings on to the console so the user knows what the outputted numbers mean. Compute surface area on one line, computed volume on the next line, computed weight on the last line, and all output must be left aligned. And no output shall exceed 90 characters including blanks. By the way, this is a requirement in all your labs. No outputted line can exceed 90 characters because then horizontal scrolling is required, and that's a difficult thing to do when you are looking at the output. So let's do the input mapping first. Simple mathematical analysis of the problem statement tells us that we need the following user inputs to compute surface area and volume. We need the length of the cuboid, we need its width, and we need its height. But to find the weight, we also need the density with the material of the cuboid, and we're going to assume that cuboid is actually solid. There are no hollow portions in it. Next slide shows that we choose meaningful names for input variables, and these input variables are stored in the RAM of the computer during the program execution, and then formulas to compute surface area, volume, and weight uses these variables and the values stored in them. So this part is that we decide what inputs are being made, and we find the names for the variables for these inputs. In programming technology, anything you need to compute in the program have to be stored first in variables. Variable naming for inputs is very important. If we choose variable names as single letters, then documentation may have to explain what they are. Modern compilers can handle large descriptive variable names, and that reduces the need for documentation and maintenance of the documentation. So in this case, 4 inputs the user will provide will be named as follows in our program: length, width, height, and density. Notice that we did not use single letter names such as L, W, etc. because they're not as clear as full words. By word length, I know it is length of the cuboid. I don't need to write a documentation to explain what that is. If I use the word L, well then that's less clear, and then I have to have documentation to explain that's the length of the cuboid. Incidentally, compiler can handle variable names up to 256 characters, although we don't have to use that large. So do not be afraid of using larger variable names. Second part of the input mapping is assigning data types to the input variable. Assigning data types makes a transition from analysis to programming technology, programming language used, and behavior of computer itself, and real world conditions. So assigning of data type requires programming technology, language, behavior of computer, and the real world conditions. Sorry. We discussed data types for the variables in depth in chapter 3 of single ebook. See module 6 on Canvas. But here's a short introduction for the purpose of this IOAA. Numbers that cannot be anything but whole numbers are called in C++ int data type. Int is short for integer. Numbers that are dictated by real life condition that they can contain decimal parts are called in C++ floating point types. Double is a precise form of floating point data type, and anytime we need to use real numbers, at least in CS1 in this class, I'm going to use double data type. Information on this slide and previous slide where we chose the name. In this slide, we have these rules for data type selection. Allows us to build an input table. And that's my input table. I have variable name in first column, C++ data type for that in the second column, and any remarks or comments I would like to make in the third column. It's a good idea to have this table as complete as possible, not leave out any rows and columns empty. try to fill it out as much as you can. And rules for variable naming are discussed in chapter 3 of single ebook. These are followings: that variable name can only contain letters, digits, and an underscore. They cannot start with a number. They cannot be a C++ reserved word, and they cannot have blank spaces. And we can see that these variable names follow all these 4 rules. And now in a minute we'll talk about data types. Choice of data types. The question one can raise now is that why did we choose double or floating point data type for all the variables such as length, width, etc. Look at here. I'm choosing double data type for all 4. This question can be answered by asking another question below. Can we force all real life cuboids to have dimensions and density in round numbers? Round number means it will have only whole number, no decimal parts. Well, answer to that is an emphatic no, we cannot. Therefore, using double data type is a logical choice. Understand that such will not be the case for these type of data, like number of students in a class. You cannot have 10 and a half students in a class. You have either 10 or 11. Or age on the last birthday. For those data, int data type is suitable because number of students in a class cannot contain decimal parts. So be very careful in your early part of programming that you clearly understand where to use int data type and where to use double data type. There are other issues with those 2 numerical data types. Please read chapter 3 to understand those issues. To avoid labor of choosing proper data type, novice programmers often use floating point data type for numbers all the time. That is an unfortunate practice because not only that may result in memory inefficient programs, but also may slow down mathematical computations in some cases. Now we need to map output variables. If we perform computations using numbers that are real numbers, floating point type, then it is certain that our output would in most general cases would be a real number as well. Thus it is clear to us that outputs such as surface area, volume, and mass would also be floating point data type. Table in next slide gives us the mapping of output variables. I just chose the name surface area. I could use SA, but that is less descriptive. I chose the name volume for volume. I could use VOL, less descriptive, and then I chose the mass. And these are double type also because there is no way I can force them to be round numbers. And then I have remarks. Once again, you have to make output variable table for your IOAA. Make sure all the rows and columns are filled out and nothing is left empty. Okay, analysis. Analysis basically, how can we go from input to output? That's analysis. In this software problem, going from input to output simply requires use of math formula for surface area volume for a cuboid and using density to convert volume to mass. In formula, we always start out with math form, and this is a very important warning to every novice programmer, which I think most people are in this class. Math form is not usable in computer programs. Okay, let me say that one more time. Math form is not usable in computer programs. So we'll show math and then C++ form that is usable in computer programs. And input variable will be used only in the right side of the computational expression to compute output variables. You will see shortly why math form of formula falls short and are not acceptable in programming. So here I put the output variable name volume, surface area, and mass. Math form of the formula: volume equal to length multiplied by width multiplied by height, and then surface area is twice of length into width plus length into height plus width into height, and mass is simply volume multiplied by density. So let us one by one see the translation to the C++ form. Before we do this translation, at least in this case, we should focus on this issue. This issue is again revisited in the next slide. Symbol X or even dot are not allowed as multiplication operators in computer programs. The expression X parentheses Y parentheses is still a compile error because binary multiplication operator asterisk is missing between X and Y. X is not used for multiplication, dot is not used for multiplication, asterisk is the one that is used for multiplication. So from going math to C++ form, I replace first X with asterisk, second X with asterisk, and that's my C++ form. Computer program will not accept that, computer program will accept that. Now, same thing, the second formula, surface area on the left hand side, this X got replaced by asterisk, this X got replaced by asterisk, this X got replaced by asterisk, but then two parentheses, this expression is still not valid, so we need to still put an asterisk in between 2 and the parenthesized expression, and this one is of course pretty simple. Mass is volume into density, mass is volume asterisk density. So that's the way to convert math form into C++ form. And you're expected to demo that in the table for IOAA for your assignment 1 and subsequent assignment. We're going to talk about this issue a little bit more in the next slide. Difference between math and C++ forms of computational expression. Notice that there is a world of difference between math and C++ form of computational expressions. Let us discuss two main differences for now. A math form could be volume into length x, width x, height. That is in C++ source code written as volume equal to length asterisk width asterisk height. Why? The reason is that letter x could be a letter in the variable name. Computer has no way of knowing whether that's the case or not. Thus, universally in all programming language, asterisk is used as a binary multiplication operator. So this is very important, so let me say this again. Computer has no way of knowing whether x is a variable name or not. Universally in every programming language, asterisk is used as a binary multiplication operator. Dot or x are never allowed as multiplication operator in programming languages. Unfortunately, novice programmers have struggled with this paradigm shift for quite a while. Only using parentheses between two operands does not do the multiplication. What shocks novice programmer even more, that below is a compile error. If I just put 2 here and then an expression parenthesis, that is still a compile error. Compile error means computer does not understand what it means. That is because computer does not do any computation unless it sees a binary multiplication operator between two operands. So there's one operand here, other operand is parenthesized, and computer is not seeing a multiplication operator between them. The red expression above 2 and expression parentheses are not seen as two operands to be multiplied because multiplication operator asterisk is missing. Thus, correct expression in C++ form can only be 2 asterisk and then the expression in the parentheses. This is very important for die-hard math people. Please, please, please understand, programming is not a math class. It's not. We use a highly modified form of math, and please get used to that. Thank you. Algorithm. Now we come to the most important part of IOA, the algorithm. Algorithm is the foundation of the bug-free software. Errors in algorithm quietly pass into software. In fact, there was a bug, a logical error, in a very popular binary search algorithm which was not detected for 60 years. 60 years. It was hidden, it lay dormant, it was not detected. Because somebody messed up the algorithm, basically. We can see that algorithm would require following high-level steps. These are variable declaration. We did that in input and output table. But then after that, we have to do that in algorithm again. Getting user input for variable that are in the input tables. And we do the same thing for the output variables. We declare them, and then we compute output variables based on the math C++ formulas, and we display output variables. Above steps will get more and more complicated as software is required to do more and more work. We write algorithm as pseudocode. We will use pseudocode language to write algorithms. This whole I/O development exercise is an exercise in designing programs. Every design activity improves with experience. No design ever is perfect when done first. Go look at the first cell phone. You'll be shocked to see how clumsy it looks today. In CSCI1 class, one inflexible rule is that all lines of algorithm must be numbered. Numbering scheme is simple for now. When it should get more sophisticated, we'll show you how to do that. Points will be deducted if algorithmic steps are not numbered. Because I have experience in designing software, I would be able to write algorithm for this software easily, but do not be discouraged if you make mistakes. In time, you will improve. So this is the algorithm for cuboid software. First, we do the variable declaration, and notice I'm actually doing the name and data type, and when we write the source code, this will reverse. Declare length as double, declare width as double, declare height as double, declare density as double. Notice that each variable has its own declaration line. Lumping into one line is not allowed. That would cause confusion when source code is written. If somebody would lump 3 or 4 variables declaration in one line, I will take off points, because that practice is discouraged. Even though it's allowed in C++, we do not allow that practice in CS1. Declare surface area as double, volume as double, declare mass as double. This declares all my variables that I'm going to use in the program. Then I take user input by prompting user to input certain data, and I store them in named variable. I prompt user to input length, and then I get that input and store in variable called length. I prompt user to input width, and I get and store that into variable called width. I prompt user to input height, and I get and store that into variable height, and then I prompt user to input density, and I get and store in variable called density. Notice that each action that would become a source code statement has its own line. Prompting will be one line, storage will be another line. Prompting will be one line, storage another line, and so on. Lumping, cutting out steps is not allowed. Clarity, even if it makes writing much longer, is most important right now. Clarity cannot be victim of speed or time saving. I will take points off if lumping is done and clarity is reduced. Notice that we used exactly the names, including the case of letters that we declared in the input table and used in C++ and math formula. No changes to names or even case of letters is not allowed. C++ is a case sensitive language. If you have length, word length, L is in uppercase, replacing with lowercase is a compile error. That's not allowed. So now we do the computation and volume. This is exactly same as we did in the analysis, the C++ form. So C++ form of formula is pretty much copied and pasted into the algorithm. And we had that for surface area, we have that mass equal to volume and density. Now here the sequence becomes important because mass expression uses volume, so computation of mass can only be done after volume has been computed. Okay? So if a computed variable is used later, then it can only be used after it has been finished computing. Now, last part of the algorithm is outputting the results as per output specification in slide number 3. So, action of outputting is called print. So we say print, comma, and if anything is in double quotes, that is printed as is. Anything in double quotes is called a string. This string will be outputted literally. Text to be outputted as is, literally. Okay? Comma, this is the variable surface area that we would like to output. Remember, I computed surface area using this formula. So when I say name surface area, computer is going to get the computed value stored in this variable and output. So this surface area and this surface area have nothing to do with each other. This is the name of variable which has the value. This is just a string. And then end of line EOL, because one of the requirement was that each print statement should be in its own line. Okay. Then second will be print comma volume of cuboid. This is the output of the text as is, and the variable volume stores the volume of the cuboid. UL means end of line, and then print mass of cuboid. This is printed as is. Mass is a variable storing the mass, UL, and end. This is the end of the algorithm. Understand that word print, after word print, each part of the output is comma separated. Comma, 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 UL, okay? You'll get used to this after some practice. More on pseudocode algorithm. Understand that algorithm pseudocode does not bother at what includes you need to do. That is your additional responsibility as a programmer when you write the source code. A very important requirement is to make algorithm as free from programming language as possible. Therefore, in this class, points will be deducted if any of the below are used in algorithm or pseudocode. Semicolon is not allowed. C in or arrow arrow not allowed. C out or arrow arrow not allowed. ENDL is not allowed. Parentheses or curly braces are not allowed. A little bit later parentheses can be used, but curly braces are never allowed. The reason for above requirement is that algorithms should have no dependency on program language to be used later. Using an algorithm, I can use any programming language I want. Visual Basic, C++, Java, or anything. I say this very boldly, programming languages are dime a dozen. They come and die, but algorithms are immortal. Anything immortal cannot be made dependent on something that is mortal and something that is going to die. Conversion from pseudocode to source code rules. We'll show you a table with 22 steps to show mapping between pseudocode and algorithm, and then to source code. We'll be using following C++ rules and objects to perform this conversion. Each programming line must end with a semicolon. Rule number 1. Variable declaration done as follows. See chapter 3 of single ebook. First data type, then variable name, then semicolon. Input is done with cin, arrow, arrow, and the variable name into which input is done. Output is done with cout, arrow, arrow, item 1, item 2, and so on. And slash n is the end of the line. You can see that word print in pseudocode is replaced by word cout, and each comma in output pseudocode is replaced by left facing arrow. EOL is slash n or ENDL. Item 1, 2, 3 are comma separated output tokens in the algorithm. So with this, we show you a mapping table for algorithm and C++ source code. So I'm just going to go through line by line. These were the lines in pseudocode. These are the lines in C++ source code that we are going to type into the compiler. Declare length as double is done. Double, data type first, length, semicolon. Declare width as double is done. Word double, width, semicolon. And you can see the rest of them are exactly the same. If there was some different data type here, we'll just use that. So in source code conversion, data type goes first, name of the variable goes second, and then semicolon. You can pause the video here and look at it for a few minutes. Then my pseudocode line is prompt user to input length. Prompting is done by cout. We'll say cout. Cout arrow are always hitting the word cout. Just remember that. Enter length. Get and store in length. Cin. Cin arrow are always going away from cin. This action here stores whatever user inputs and press an enter key into the length variable. Important thing one more time. If variable name was uppercase L length in input table in formulas, it cannot change here. You cannot degrade it to lowercase. So same way, input is done for width, height, and density. Variable names cannot change in spelling or case of letters. So pause the video here for a minute and look at mapping between pseudocode line and source code lines. Then we have volume equal to length asterisk width asterisk height. This was in pseudocode. This is exactly the same way, except we do have a semicolon. Same thing with the surface area. This was the formula in the analysis, C++ form. We put exactly same thing except ending with the semicolon. Same formula as in analysis, ending with the semicolon. Now we do the print statement. For this you can go back to previous slide. So print gets replaced by cout, arrow, arrow, surface area of cuboid equals, gets outputted exactly the same way. Each comma is replaced by left facing arrow, arrow. Surface area, variable name exactly the same way. End of line is slash n in quotes, ending with the semicolon. And we have done the same thing for the next two print statement. Ending it just return 0, and we'll show you how this code on the right column is placed inside a main function, executed and run. So these are all the detailed steps for IOAA. In the next, third and last video, I'm going to pick up these 3 slides and show you how to type this in the source code, execute it, and just do different things with it. Okay, so this is the end of this video on IOA technology. Thanks again, and this is Dr. Singhal from El Camino College. Thank you.